Okay, so with that in mind, let's take a look at section 15.1. And again, I covered this in my video on YouTube. Just kind of want to go over it very quickly so that we're all on the same page before we get into section 15.2. And where we start is with amines, and amines are derivatives of ammonia. And everybody should have learned the structure of ammonia way back in Introduction to Chemistry 1. And it's very important that you know that amines and ammonia are basic, okay? They are organic bases. They're not strong bases like sodium hydroxide or potassium hydroxide, but they are bases. And I explained the difference in my video. I explained the difference between a primary amine, a secondary amine, and a tertiary amine. And that's something that we looked at even when we were first discussing functional groups. And we talked about, or I talked about in my video, about the molecular geometry of all amines, primary, secondary, and tertiary, which is the same as that of ammonia in that it is trigonal pyramidal. And the bond angles in here, whether it's in ammonia or in an amine, all you have to know for Chemistry 102 is that they are less than 109.5 degrees. And the reason that they are a little bit less than the tetrahedral bond angle of 109.5 degrees is because there is some repulsion due to this lone pair not participating in a bond. So those electrons are not shared, right? Not shared, unshared electrons. And so what they can do is they can repel the electrons in the three bonds and kind of push them together a little bit tighter. Some books will say it's 107 degrees, but as long as you say less than 109.5 degrees, that's fine with me. Then I talked about what a primary, secondary, and tertiary amine is. So I've gone over that. And then I talked a lot in my video about hydrogen bonding, and we looked at the requirements for hydrogen bonding a few times in this class, and that you either need a bond between oxygen and hydrogen, nitrogen and hydrogen, or fluorine and hydrogen. And of course, in this chapter, we're focusing on the nitrogen-hydrogen bond. And the reason that amines do form hydrogen bonds, but they are not as strong as the hydrogen bonds found in alcohols, so those found in alcohols like this, is simply because nitrogen is less electronegative than hydrogen. So if I look at the oxygen-hydrogen bond, oxygen has an electronegativity of 3.5, hydrogen is 2.1. So therefore my difference, or my delta electronegativity, is 3.5 minus 2.1, which gives us a difference of 1.4. And so we have the dipole going towards the oxygen, all right? But if we look at the hydrogen bond between hydrogen and nitrogen, hydrogen has an electronegativity of 2.1 and nitrogen is 3.0, and therefore our delta En is smaller. So that dipole is not going to be as strong. And I said there's a variety of ways you could represent that. I'll just put a smaller dipole, okay? Just not quite as big. And this is why primary and secondary amines, although they do have hydrogen bonding, their boiling points are not as high as those of analogous alcohols, and it's simply based on the electronegativity of the nitrogen atom. And then I also said that tertiary amines cannot hydrogen bond with each other. And why would that be? The reason why is because tertiary amines do not have NH bonds. They have no nitrogen-hydrogen bonds, right? A tertiary amine has alkyl or aryl groups attached to the nitrogen. Okay, so that covers that. Then what else? In my video, I spent quite a bit of time talking about boiling points, and that amines have boiling points somewhere between those of alcohols and alkanes. And again, we say, okay, something like propane has no hydrogen bonding. It has no dipole-dipole force. The only intermolecular force that propane experiences are London forces, which are the weakest of all the intermolecular forces. Then we have ethanamine and ethanol, which have similar molar masses. They can both participate in hydrogen bonding, okay? But what's the difference? Is that the hydrogen bond in ethanol is stronger, okay? And the one in the amine is weaker. And again, that's based on electronegativity. All right, and then we looked at the difference in boiling points between a primary amine, like propylamine. So this is a primary amine, then a secondary amine, and then this tertiary amine. And all three of these amines are isomers of each other. They all have the same molecular formula, which is C3H123456789, C3H9N. And we see that the primary and secondary amines have much higher boiling points than that of the tertiary amine. And it's because the tertiary amine does not have hydrogen bonding. There are no nitrogen-hydrogen bonds in trimethylamine. And I spent some time talking about this table, and I'll let you make sure that you watch the video to catch all the news on that. And then I spent some time just looking at this briefly and comparing the boiling points of an alcohol and the analogous amine. So methanol is CH3OH and methanamine is CH3NH2. And you can see they have very similar molar masses, but their boiling points are very different. And again, it's because of the stronger, we'll put here stronger hydrogen bonding. Okay, and again, in my video, I talk about the entire table. So make sure you catch all that. And then I looked at this example, and we could just take a look at one example here. If we compare the last two compounds, it says propylamine or butane. Which one of these will have a higher boiling point? Well, if I draw butane, that's 1, 2, 3, 4. So there's butane. And if I draw propylamine, I have 1, 2, 3 carbons, and then my amino group. Well, I think you would all guess that propylamine is going to have a higher boiling point. And why is that? It's because propylamine can participate in hydrogen bonding. And butane only experiences London forces because it is a hydrocarbon. Okay? And just to review this one last time, we know that in terms of intermolecular forces, right? Intermolecular forces, if we go from strong to weak, okay, the weakest of all the intermolecular forces are those London forces. Then we go to dipole, dipole, dipole. And then, of course, the hydrogen bond is the king of the castle, H bond. There we go. Okay, then from there, I talk about solubility, and I said that all amines can form hydrogen bonds with water. And there's a water molecule shown here. And you can see here's a primary amine hydrogen bonding with a water molecule, and they're showing the hydrogen bond here. And it says here that as a rule of thumb, amines up to 6 carbons are generally going to be water soluble due to hydrogen bonding. And of course, just like we saw with alcohols, that as the carbon length or the hydrocarbon portion of the molecule, as the length of that portion gets bigger and bigger and bigger, water solubility will decrease. And nothing really new there. Then I spent some time on nomenclature, and hopefully you spent some time practicing this over the weekend. It takes a lot of practice to learn how to name amines. The good news is that primary amines, primary aliphatic amines, are much like naming alcohols, okay? We'll put here like naming an alcohol, in that you find the longest continuous chain that contains the amine group, then you drop the E at the end and you replace it with amine. So instead of something like butane, you would remove the E and then you would end up with butanamine, okay? Like that. So we have propanamine, butanamine, pentanamine, hexanamine, so on and so forth. Then we number the parent chain to give the amine carbon the lowest possible number. So we want to give the carbon with the amino group, we want to give that the lowest possible number, and then we name all our substituents and number them as usual. So 1-methyl, 2-ethyl, 3-pro, whatever, okay? Whatever substituent we have. Now, of course, in the case of methanamine, there's only one carbon that can be substituted, so we just leave out the number. So we call that, instead of methane, right, CH4 is methane, so this becomes methanamine. And then when we have propanamine, we have to provide a number or a locant, which is sometimes called, because there are two places you could put the nitrogen or the amine group on the propane chain. Say, for example, we had 3 carbons like this, CH3, CH, CH3. We could also have the amine group here. And this would be, I'll make a little line here, this would be 2-propanamine. Okay, and this next one is 2-pentanamine because we numbered the longest carbon chain, which is highlighted in yellow, so that we give that amine group the lowest possible number. Then I talked about naming secondary and tertiary amines, and you're going to have to watch the video on this because if you're hearing this for the first time, you'll have to go back because time marches on for whom the bell tolls. And it says the prefix N-alkyl is added to the name of the parent for secondary and tertiary amines. So again, we find the longest carbon chain, and whatever alkyl or aryl group that we have on there, we name it N, whatever that group is. So here's the longest carbon chain in this molecule. It's an ethyl group, right? So if we have this molecule, CH3CH3, that is ethane, and since I have an amine on here, it's ethane amine. So we've got that part, and then we have a methyl group. We don't call it methylethanamine. We say N hyphen, so capital N hyphen, methyl ethanamine. The same thing applies here, and you're probably like, well, I watched the video, and I already know the common name for this is trimethylamine. Yes, that's a common name, but these are IUPAC names, okay? IUPAC names. And again, the longest chain here is 1 carbon, and it wouldn't matter which one you boxed in, really. But I have methanamine, and I have 2 methyl groups, so I say NN-di. Okay, so I have to put the capital letter N for every substituent that I have, every alkyl substituent I have on there. With, excuse me, with aromatic amines, again, I'll let you watch that in the video, and I talk quite a bit about aniline. And aniline is a compound that you had to memorize for the first exam, I believe. And I mentioned the substitution on the nitrogen of aniline as well. Excuse me. All right. Common names of amines. When we're dealing with really small amines, common names are very popular. And all we do is list the alkyl groups in alphabetical order, and we follow them by the word amine. Couldn't get much simpler than that. If the name is continuous, we leave out spaces. So here we have a methyl group, so we call it methylamine. If we have 2 methyl groups, we call it dimethylamine. If we have 3 of them, trimethylamine. If you have an ethyl group, we'd call it ethylamine. And if we have 2 groups, well, you list them in terms of alphabetical order. So you put ethyl, E, and then methyl, ethyl methylamine. So let's say you had something, let's say you had something that looked like this, where you have a methyl group, an ethyl group, and a propyl group. How would you name that? You would call this ethyl methyl propylamine. Okay, that's what you would call it. That would be the common name. All right, so alphabetical order for the common names. And then I spent some time talking about amphetamines, and if you want to understand about crystal meth and where methamphetamine comes from, you have to understand a little bit about amphetamines. So I talk about those in very little detail. And then I talk about ephedrine and pseudoephedrine and phenylephrine. And pseudoephedrine can be converted into crystal meth very easily, in fact. And that's why things like Sudafed is held behind the counter at the pharmacy, even though it is an over-the-counter medication. They monitor the drugs coming and going, because all you have to do is remove this portion of the molecule there, and then you would have crystal meth. So very easy to make crystal meth from pseudoephedrine. And of course, the pharmaceutical companies are always trying to find ways to mitigate people's ability to convert, decongestants into illegal drugs. And so they came up with phenylephrine, which is very difficult, if not impossible, to convert into methamphetamine. Anyhow, and sulfa drugs, if you go all the way back to the Second World War, a lot of soldiers' lives were saved by the sulfur drugs, which are antibiotics. They're among the first antibiotics that were ever developed, and you can see that they have nitrogen atoms in them. All right, preparation of amines. So aliphatic amines are so here we go. We're talking about reactions now. So we talk about the preparation of an amine, and that can be affected by the reduction of an amide. And the way we do that is we treat that with a source of hydrogen atoms, so some kind of reducing agent. And so what you see here, the H in the square brackets, let's see here, H in the square brackets, you can just think of that as being a reducing agent, because in organic chemistry, reduction is gaining what? Gaining hydrogen or losing oxygen. And you can see that both of those things occur in this reaction. Not only do we lose this oxygen, but we gain these 2 hydrogen atoms. So this is a what? It is a reduction. So you reduce an amide or a nitro compound. And I told you earlier on what a nitro compound is. And this is a reaction that I've done many, many times in my life, is taking a nitro compound, treating that with a reducing agent. And again, we lose oxygen and we gain hydrogen to reduce that nitro compound to an amine. When I was working in HIV, I did that reaction, I don't know, probably 100 times or something, a long time ago, maybe 15 years ago. Anyhow, earlier on, I think in the first or second slide this evening, I mentioned that amines are weak bases. And what is a base? A base is a proton acceptor, so they're H plus acceptors. And you would have learned all about acids and bases way back in Introduction to Chemistry 1. So if we take an amine and we put it in water, the amine is a base and it can accept a proton from the water molecule in order to form an alkyl ammonium ion and hydroxide. And that's why when you take an amine and you make a solution of it in water, that's why when you test it with pH paper, it comes out basic, because you're producing hydroxide ions. Next is an example of the basicity of amines. I'm going to go over that. And then neutralization reactions. Since an amine is a base, it can react with an acid like hydrochloric acid to make an alkyl ammonium salt. In fact, this is the reason why people initially started putting lemon juice on fish, because when fish begins to rot and become putrid, it will produce amines, and amines are what gives you the fishy odor. So amines have fishy, like horrible fishy odors, you know. So if they put lemon juice on it, so lemon juice is an acid, and what it would do is it would protonate those stinky bases, those unpleasant odors, and convert them into salts. And salts, generally speaking, have very high vapor pressures, right? You don't think of a salt as being a liquid, okay? So what they would do is they would mitigate those odors by converting the amines into salts. Anyhow, we name, and I talked about naming amine salts, and I explained how to do that, and I'm not going to go over that again, so I'll give you time to take a look at that. And I talked about what a quaternary ammonium salt is, a quat, which are found in scope and all those kinds of things. Anyhow, so that covers, that's a very quick, that's a 20-minute, you know, kind of pass over section 15.1, but I know you all watched the video at least 3 times because I got a big check in the mail from YouTube. I'm kidding. Anyhow, so there we go. So that is the end of 15.1. And I'm going to stop